Welcome to Cary Pathshala, a novel initiative of the University of Kerala to archive educative videos. CLIF is taking part in this venture wherein we are exposing the instruments being housed in the CLIF campus for the benefit of people who want to use the facility for their research purposes. The facility is managed by qualified technicians, highly trained, as well that governed or managed by faculty who are all experts in the field. The idea behind housing all the instruments under one roof is that not only that you will be able to use the instrument, but also get the feel of how exactly an instrument is functioning. For that matter, we are encouraging people to come to CLIF while their samples are analyzed so that they will be able to understand how the instrument is functioning to get the desired results. We have qualified faculty as well as outside experts who will be speaking during the video filming on the application value of each instrument being housed in this. The central instrumentation facility, which is being housed in the Cary campus, has got about 21 equipments, high-end equipments, being supported by different organizations in the country. I'm not going to the details of the functioning of the instrument as is going to be demonstrated in the videos. So I welcome you to view the videos, and straight away we see the videos about the functioning of the instruments which are housed in the CLIF campus. Thank you very much.
Hi everyone, welcome to the Cary Pathshala video program arranged by the Central Laboratory for Instrumentation Facilitation. Myself B. Upendra, working as a scientist at National Center for Earth Science Studies. My research interest is water and environmental research related problems. I am here to discuss about the ultraviolet visible spectroscopy, also known as UV visible spectroscopy. So typically the UV visible spectroscopy will be used for extracting the chemical information of colored compounds, colored materials and organic compounds, where they have the lambda max value between 300 to 800 nanometer. Now let's get into it. So ultraviolet visible spectroscopy typically will have one light source. That light source will be made as monochromatic by using the gratings. That light will be sent through the sample. The transmitted light from the sample will be detected and will be displayed by using the software program. So that whole setup typically looks like this. So coming to what is UV visible light. So UV visible light is the part of the electromagnetic radiation which is in between 300 to 800 nanometer as shown in the picture. Further, coming to the basic principle which explains the UV visible spectroscopy is as follows. Okay, the UV visible incident radiation will pass through the sample. Sample can be a chemical material or any organic material compound. So that part of the radiation will be absorbed from the sample, part of the radiation will be transmitted, and the part of the radiation will be reflected, fluorescent scattered. The part of that light which is transmitted from the sample, that is attenuated after some time. The measurement of this attenuated light is nothing but the UV visible spectroscopy. So that measurements will do it according to the basic principles of Lambert's law, where the concentration of the analyte is more, the absorbance will more. That means the attenuation light will be more. So the attenuation light will be maximum at a particular wavelength. That wavelength is called lambda max. This lambda max will be corresponding to the each characteristic of that chemical material. So finally, this UV visible spectroscopy helps in characterizing the absorption and transmission of the light. With this transmission of light, we can identify chemical compounds, materials which are basically having some color and which can absorb the lambda max value between 300 to 800 nanometer. The entire setup will look like as follows. We have one chemical material, and chemical material, the incident radiation will pass through chemical material. The emitted radiation will be detected by using the photodiode or phototube, or typically a PMT, photomultiplied tubes nowadays, and we'll have a signal noise process after that. Now we discuss some important applications of UV visible spectroscopy. The first one is the quantitative analysis using this UV visible spectroscopy. This quantitative analysis is typically for the metal salt solutions which are colored in nature, for example copper 2, iron 2, nickel 2, and some organic colored compounds. that can be easily quantified by using the Beer-Lambert's law. In the Beer-Lambert's law, what we do is we measure the OD, optical density, with respect to the concentration. We prepare a standard calibration graph with 1:1 line. Then for the unknown samples, we measure the optical density of the unknown sample that will be plotted on this graph, and we'll measure the concentration as shown in the picture. And second application is typically the qualitative analysis using this UV visible spectroscopy. The qualitative analysis of visible spectroscopy involves identification of the functional groups. With this UV visible spectroscopy, we can identify the some of the functional groups. Since each functional group will have a characteristic lambda max value, that lambda max value will be corresponding to only one functional group. For example, lambda max of acetic acid COH functional group will be around 276, whereas the lambda max value of peptide bond, amino acid bond CONH2 amide bond will be around 248 nanometer. That's how we can differentiate between functional group. And third application will be distinguishing between the cis and trans isomers, that is geometrical isomers. So again, each geometrical isomers will have its own characteristic lambda max value. Based on that, we can differentiate by measuring the lambda max value of each compound. For example, as shown in the example in the right side, the cinnamic acid exists in cis and trans forms. First, the trans form, the lambda 1 value will be around 264 nanometer, and the cis isomer will have the lambda 2 value around 270. That's how we can differentiate the cis and trans isomers. And fourth application involves the finding the rate constants by using this UV visible spectrophotometer. We can typically find the rate constant for any order, 0, first and second order reactions. Here in the example, I have shown you the first order rate constant k equal to 2.03 by t into log of a by a minus x, where a is the initial concentration and a minus x is the final concentration after some time t. So typically what we do here is we'll find the calibration graph by measuring the optical density versus concentration of a known sample, of an analyte A, and then we make the possible intent reaction. After some time x, we again measure the concentration A minus x. So this is like measuring the optical density before and after reaction. By plotting that before and after reaction values, we can find it out the concentration of A and A minus x. I guess this helps you in understanding the UV visible spectrophotometer, and thanks for it.
Hi, welcome everyone to a wonderful session about spectroscopy. I am Vishnu P, Technical Officer, Central Laboratory for Instrumentation and Facilitation, University of Kerala. The CLIF is a new and exciting initiative with number of analytical instruments under various schemes. The center represents one of the largest commitments for research in the history of the university. Today, we can discuss about an interesting topic called spectroscopy. As we all know, the human ear can hear only a certain frequency of sound. Likewise, the human eye can see a certain kind of light. The light that we can see is referred to as the visible spectrum of light. Beyond the visible spectrum is the ultraviolet and infrared lights. Although these lights cannot see directly by the human eye, certain devices can detect them. UV visible NIR, FTIR, NMR, fluorescence spectrometer are some of the spectroscopic instruments, whereas spectroscopy is a branch of science deals with the study of interaction of electromagnetic radiation with matter. Here we are going to discuss about such a spectrophotometer called UV visible NIR spectrophotometer. UV visible NIR spectroscopy is considered as the most significant spectrophotometric procedure commonly used for the examination of different types of compounds. Here, we can analyze the UV region, visible region and the NIR region. It can be performed in both transmission and diffuse reflectance modes, with transmission preferred for aqueous phase reactions or samples and diffuse reflectance for solid samples. Here we are using Cary 5000 Agilent technologies which ranges from 175 nanometer to 3300 nanometer. The spectral optical isolation system breaks all the noise barriers and provides better performance integrated by a modular Windows-based Cary WinUV software makes it easy to perform powerful analysis. Source. Here we have three sources. Deuterium lamp for the range of 200 nanometer to 400 nanometer. Then tungsten lamp for 400 nanometer to 800 nanometer and incandescent lamp for the range of 800 nanometer to 3000 nanometer. Then monochromator. Double out of plane litho monochromator is used here. Its function is to pass a selected bandwidth of light towards the beam splitter. Then we have the beam splitter. They help to split the beam towards sample as well as reference. Then after that the sample compartment. Then after that the detector. R928 photomultiplier for UV visible range and Peltier cooled PBS photocell for NIR range. Then software. Windows based Cary WinUV software is used as the running software for UV. The large compartment can be expanded to hold large accessories and integrating spheres for spectral and diffuse reflectance. The integrating sphere for spectral and diffuse reflectance measurements is 110 mm module and the variable slit width down to 0.01 nanometer for optimum control over data resolution. The sample compartment is large in size and have a lockdown mechanism for quick changes and positioning. Nature of the sample. We can use powder samples, thin metal pieces, thin films and also liquid samples for UV visible NIR. Working principle. UV visible NIR spectroscopy is associated with the interaction of light with the matter. Since the light is absorbed by the substance or matter, the resultant energy content of atoms or molecules increases. The absorption of ultraviolet or visible light by an analyte will generate a specific spectrum while ultraviolet radiation is absorbed. It results in the electrons' excitation in the state of high energy from the ground state. The theory that revolves about this concept suggests that the energy absorbed by ultraviolet radiation is equivalent to the energy difference between the ground and high energy state. UV spectrophotometer principle adheres to the Beer-Lambert's law. This law expresses that when a beam of monochromatic light is gone through a sample solution and absorbing analyte, the diminishing rate of the radiation power alongside the thickness of the sample solution is really corresponding to the incident radiation and solution concentration. That is, there is a linear relationship between the concentration and the absorbance of the solution. Beer-Lambert's law is expressed through this equation: A equal to ECl or A equal to epsilon Cl, where A is the absorbance, epsilon is the molar absorption coefficient, C is the molar concentration and L is the optical path length. It is clear from the Beer-Lambert's law that the number of molecules able to absorb the light of the specified wavelength, the light absorption limit is high. This is the fundamental principle of the UV spectroscopy. Here we are analyzing powder samples as well as liquid samples. For powder samples, we are using this powder sample holder, and for liquid samples, we are using the quartz cuvette. Here, now we are going to analyze a powder sample. that is in the diffuse reflectance mode. For that, initially we have to load a reference. This is the reference, it's Teflon. Now we can load this reference to the sample loading portions. We have to load it here. Then tie the screw and cover it with the black cloth. This is to avoid the stray lights. After that, we can run the reference. Open the Cary WinUV software. Wait for some time to become online. Then take setup, Cary options. Then we have to select the run parameters in the X and Y axis. And then we have to give the start and stop range. Then go to the advanced settings and set bandwidth as 4. Then give the independent control. After that, select baseline and then baseline correction. OK. Then wait for some time. Baseline is active. Select the same and confirm the reference is loaded and press OK. Now the reference scan is started. Now the reference scan is completed. After the reference sample analysis is over, we have to clean the cuvette with IP. Then take the sample to be analyzed. Fill it to the sample holder. Now the sample is inside the sample holder. Close the sample holder. The sample should cover the entire portion of the sample holder here, like this. Now we can load the sample to the instrument. Now the reference run is over. We can remove the reference and load the sample. First, remove the black cloth, then unscrew, take the reference out. Then take the sample and load the sample. Tight the screw, cover it with the black cloth. Then run the sample. Then start the run. Select the location and give the name and save. Then OK. Now the sample run is started. The wavelength is measured in x-axis and the corresponding percentage reflectance is measured in y-axis. Now the sample analysis is completed. We get a wavelength versus reflectance plot. We can convert this into wavelength versus absorbance plot through mathematical calculation. Hence, we can calculate the lambda max value. There are so many advantages while using this technique. They are highly accurate and very simple to operate. It is cost-efficient instrument because we have only initial cost for the instrument. The consumable cost is very less. It covers the entire of UV, visible and NIR region and provides robust operation. It can be used in the degradation study of drugs. For all techniques have advantages as well as disadvantages. The disadvantages include the result of the absorption can be affected by pH, temperature, contaminants and impurities. It takes time to get ready to use as it has a stabilization time. We have to clean the cuvette after each sample analysis. This cuvette handling can affect the reading of the sample. Stray lights from outside as well as inside the lab may affect the results. Now we can discuss some of the applications of UV-Visible NIR. This can be used for the qualitative and quantitative analysis, that is, used for the characterization of aromatic compounds and can be used to find out molar concentration of the solute under study. Then, detection of impurities, that is, the impurities in organic solvents by comparing with standard solvent. Detection of functional group by checking the absence of a band at wavelength regarded as an evidence for absence of group. Examination of polynuclear hydrocarbons. Structure elucidation of organic compound, that is, the presence or absence of unsaturation, the presence of hitherto atoms, etc. Molar weight determination. Biochemical and kinetic studies of liquid samples. Application in life science and pharmacy. With this, we can wind up this session. Thank you.